We discussed in the previous video why we would be interested in finding out what stabilizes a carbocation, so in this lecture we're going to take a look at that. First and foremost, R groups help to stabilize a carbocation. What I mean by that is if you have a positively charged carbon, a carbocation, the more R groups there are around that carbon, the more stable the carbocation will be. So when we have a carbocation that has only R groups around it, so 3 R groups, we're going to call this a tertiary carbocation, and that's going to be the most stable type of carbocation that we can have. When you have only 2 R groups and then 1 hydrogen there, this is a secondary carbocation, a little less stable. When you have only 1 R group and 2 hydrogens, this is a primary carbocation. And then finally, when you have only hydrogens around the carbocation, this is going to be just a methyl cation, and this is the least stable of all. There are really 2 reasons why R groups help to stabilize a carbocation. The first of those is an inductive effect. So if you recall, carbocations are sp2 hybridized, and these surrounding R groups are going to have sp3 carbons on them. And there is an sp3 carbon consists of a 25% s, 75% p orbital character, while sp2 is about 33% s and 67% p. It's this difference in percent s character that's going to cause a slight inductive effect. The higher the percent S character, if you recall, we discussed this somewhat when we were talking about acidity, but the more electronegative the carbon. And so an sp2 carbon is slightly more electronegative than an sp3 carbon, and so you're going to get electron donation coming in from these sp3 hybridized carbons. The second reason that R groups help to stabilize a carbocation is a little bit abstract, but it's something called hyperconjugation. And this diagram is actually directly out of the textbook. They do a much nicer job of drawing pictures than I do. But if you take a look at a carbocation that has only hydrogens around it, so this would be a methyl cation, as opposed to a carbocation that has an sp3 carbon on it, what you notice is the sigma bond of the CH bond on the neighboring R group can actually donate some electron density here through space, and that's going to help to stabilize the carbocation. So you can imagine each one of these bonds is able to do that. And if you look over here, this CH3 group could do the same thing. And so the more of this hyperconjugation that can take place, the more stable the carbocation will be. It's basically helping to alleviate that carbon of some of that positive charge. The second factor that can play into carbocation stabilization is solvation. A highly solvated carbocation is going to be more stable than a carbocation that's not solvated. And what I'm showing here are the solvent molecules interacting through intermolecular forces. So these are solute-solvent intermolecular forces, and this is going to help stabilize the carbocation as well. There are 2 types of polar solvents that we will come across in this class. There are, of course, nonpolar solvents as well, but we're going to see that most reactions that we will study will take place in relatively polar solvents. First is what's called a protic solvent, and this type of solvent can donate and accept hydrogen bonds. And then there's aprotic solvent, which cannot donate hydrogen bonds, but may or may not accept hydrogen bonds. Protic solvents can solvate carbocations very well, and that's key here. And the 2 most common type of protic solvents that you're going to see in this class are going to be water and alcohols. They both have a hydrogen here that can be involved in hydrogen bonding, and they also have oxygens that can accept hydrogen bonds. But the reason that they're protic is because of the proton here that can be donated for a hydrogen bond. So what you're going to get when you put a carbocation into a polar protic solvent like water, for example, is this extensive solvation of not just the carbocation itself, but also its counter ion. And so it's helping, the polar protic solvent is helping to separate the carbocation from the carb anion, and at the same time it's highly solvating the carbocation and helping to stabilize that positive charge.